Here, we're talking about something that might just change the way you see regression models forever, support vector regression, or SVR. Now, I know what you might be thinking. Support vector machines? Aren't those just for classification? Well, that's where the twist comes in. SVR takes the core principles of SVM and flips them into a powerful tool for predicting continuous values. And trust me, once you see what it can do, you'll wonder why you haven't used it more often. We're going to break it all down, starting with the big picture, what SVR is, how it differs from traditional regression techniques, and why it's so effective. Then we'll take a deep dive into the math behind it. Don't worry, I'll make it painless. From there, we'll explore its real-world applications, from stock price prediction to medical diagnosis, and even how businesses use it to predict customer behavior. We'll also cover the advantages, why it's so robust to outliers and works well in high-dimensional spaces, as well as its challenges like parameter tuning and computational complexity. But that's just the beginning. We'll also go hands-on with an SVR implementation in Python, tuning hyperparameters, choosing the right kernel, and evaluating performance with metrics like mean squared error and R-squared. And to make things even more interesting, we'll look at case studies, how SVR has been used in finance, healthcare, and environmental science. Finally, we'll peek into the future, how researchers are integrating SVR with deep learning and developing smarter, faster algorithms. So, if you're ready to rethink regression models and unlock a new way of making predictions, you're in the right place. And speaking of predictions, can you guess what the first slide is all about? Let's find out. Imagine you're a weather forecaster. You want to predict tomorrow's temperature, but your data is all over the place. Some points are noisy, some are extreme, and you don't want a model that overreacts to every little fluctuation. You need something precise, adaptable, and resilient to outliers. That's exactly what Support Vector Regression, SVR, does. It's a machine learning technique that finds the best possible prediction while ignoring unnecessary noise, unlike traditional regression, which just minimizes errors. SVR introduces a margin of tolerance, kind of like saying, I don't need to be perfect, just close enough. Think of it like a tightrope walker. Instead of trying to step exactly on every single rope fiber, they balance within a range, staying steady and focused. That's SVR in action. It doesn't chase every data point, but stays within a controlled space, making it robust and powerful for real-world predictions. So why does this matter? Well, SVR is used everywhere, from predicting stock prices and disease progression to optimizing marketing strategies and engineering systems. It's fast, flexible, and, when used correctly, can outperform many traditional regression methods. And the best part, you're about to learn how it all works. Ready to dive in? Support Vector regression is all about balance. Instead of just trying to fit a straight line that minimizes the average error, it introduces a new way of thinking. It says, let's not stress over every little mistake. Let's allow a bit of flexibility, a margin within which small errors don't even count. This is called the Epsilon margin, and it acts like a buffer zone around the ideal prediction line. If a data point falls within this margin, it's considered close enough and we don't need to adjust the model for it. But real-world data is messy and not every point will fall neatly within this buffer. That's where slack variables come in. These act like an allowance for points that are a bit further out but still need to be considered. If a point falls outside the margin, the model won't just ignore it, but it also won't overreact. It will try to adjust just enough to account for those points without compromising the overall simplicity of the model. There is also a trade-off between how strict or lenient the model should be. This is controlled by a regularization parameter called C. A small c allows a wider margin, meaning the model is more forgiving with errors. A large C, on the other hand, forces the model to be more precise, making it try harder to fit every point as accurately as possible, but being too strict can lead to overfitting, where the model starts memorizing noise instead of learning true patterns. The real magic of support vector regression comes from its ability to handle complex relationships in data. Instead of being limited to straight lines, it can use special functions called kernels to transform the data. A linear kernel keeps things simple, treating the data as it is. A polynomial kernel recognizes patterns in how different features interact. The most flexible option is the radial basis function kernel, which allows the model to see nonlinear trends that would otherwise be invisible. At its core, support vector regression is about balance. It doesn't just chase the lowest error like traditional regression. It creates a system where small mistakes are ignored, important patterns are captured, and the right level of flexibility is maintained. The goal is to build a model that generalizes well, meaning it makes solid predictions even when faced with new, unseen data. This careful balance of flexibility, precision, and generalization is what makes support vector regression such a powerful tool. It is not just about finding a mathematical solution, but about understanding how to model real-world data in a way that is both efficient and insightful. Now that we have built this foundation, the next step is to explore how it compares to its cousin, support vector machines, and see where the real differences lie. Support vector machines and support vector regression share the same foundation, but they serve completely different purposes. Imagine you're sorting objects into two categories, maybe apples and oranges. Support vector machines help you draw the perfect boundary between them, making sure that even the trickiest cases are classified correctly. But what if, instead of classifying things, you needed to predict something? Like the weight of an apple based on its size? That's where support vector regression comes in. The fundamental difference lies in their output. Support vector machines produce a definite answer, like this is an apple, or this is an orange. The goal is to separate the categories as cleanly as possible by finding the best possible boundary, called a hyperplane. Support vector regression, on the other hand, doesn't classify. It predicts a continuous value. Instead of finding a clear-cut division, it creates a smooth function that estimates the relationship between input and output while ignoring small variations. The way they handle errors is also different. Support vector machines focus on maximizing the gap between categories. They care most about the hardest to classify points, the ones sitting right on the edge of the boundary. Support vector regression, however, introduces the epsilon margin, where small errors are completely ignored. This is what makes it resistant to noise and minor fluctuations in data. Computational complexity also sets them apart. Support vector machines deal with discrete classes, so their optimization problem is often more complex, especially when dealing with multiple categories. Support vector regression, in contrast, can be computationally efficient, particularly when working with large data sets that require fine-tuned predictions instead of strict classifications. Support vector machines are often found in applications like image recognition, text classification, and fraud detection, where a decision must be made between categories. Support vector regression thrives in scenarios where trends and patterns need to be modeled, such as predicting stock prices, forecasting demand, or analyzing customer behavior. In essence, they are two sides of the same coin. One is a powerful tool for making decisions, while the other is built for making predictions. They share the same mathematical backbone, but are designed to tackle very different types of problems. Now that we've seen what sets support vector regression apart, it's time to explore why it's so powerful. What makes it such a reliable tool for real-world applications? Let's dive into its advantages. Support vector regression stands out because of its unique ability to handle complex data, adapt to different scenarios, and maintain precision even in unpredictable environments. Unlike traditional regression methods, which try to fit every point as closely as possible, SVR introduces a level of flexibility that makes it more robust, efficient, and adaptable. One of its biggest advantages is its ability to work well with high-dimensional data. Many machine learning models struggle when there are more features than observations, but SVR can handle this effortlessly. This is why it is often used in fields like genomics, finance, and engineering, where data sets can be massive, yet meaningful patterns still need to be uncovered. Another major strength is its robustness to outliers. In real-world data, noise and extreme values are common. Traditional regression methods are sensitive to these outliers, pulling the prediction line in unnatural directions. SVR, however, introduces the Epsilon margin, which ignores small errors and focuses only on the truly significant deviations. This means that outliers won't distort the model's performance, allowing it to stay focused on the main trends. Flexibility is another reason why SVR is so powerful. Unlike basic regression techniques, which assume data follows a straight line pattern, SVR can adapt to nonlinear relationships. Thanks to the kernel trick, it can transform data into higher dimensions, capturing intricate patterns that would otherwise go unnoticed. Whether the relationship between variables is linear, polynomial, or highly complex, SVR can find the right structure for the problem. Computational efficiency is another key factor. Traditional regression models often become slow and inefficient when dealing with large-scale datasets, but SVR remains viable even for big data problems. With a computational complexity that scales better than many other machine learning models, it can process large amounts of information without requiring excessive resources. Beyond the technical advantages, the real-world applications of SVR prove its versatility. It is used to predict stock prices, analyze consumer behavior, forecast pollution levels, model disease progression, and even optimize engineering systems. The ability to make accurate predictions while ignoring irrelevant fluctuations makes it a go-to tool for industries that rely on data-driven decision-making. Support Vector regression is not just another regression model, it is a highly adaptable, powerful approach that balances precision, flexibility, and computational efficiency. But like any tool, it has its challenges. So before we get carried away with its strengths, let's take a look at the potential downsides. What are the limitations and where does SVR struggle? Let's find out. While support vector regression is a powerful and versatile tool, it is not without its challenges. Like any machine learning model, it has certain limitations that can make it difficult to use in some situations. Understanding these drawbacks is just as important as recognizing its strengths, because the key to using SVR effectively lies in knowing when and how to apply it. One of the biggest challenges with SVR is overfitting, especially when dealing with small datasets or overly complex models. Because SVR relies on support vectors to define the regression function, using too many can lead to a model that fits the training data perfectly, but fails to generalize to new data. This is especially problematic when the number of features is very high compared to the number of observations, making it easy for the model to memorize noise instead of learning real patterns. Another major limitation is sensitivity to parameter selection. SVR relies heavily on hyperparameters like the regularization parameter C, the epsilon margin, and the choice of kernel. Poorly chosen parameters can lead to suboptimal performance, either making the model too rigid or too flexible. This means that to get the best results, extensive hyperparameter tuning is required, often through trial and error or cross-validation. Without careful tuning, the model might perform poorly, even when applied to a dataset where SVR should in theory excel. Computational complexity can also be a bottleneck. Although SVR is generally efficient, its complexity grows with the square of the number of observations multiplied by the number of support vectors. This can make it computationally expensive, particularly for large datasets. Training an SVR model on thousands or millions of data points can take significantly more time than simpler regression models, making it impractical for some real-time applications. Additionally, While SVR is robust to outliers, it is not completely immune to them. If the regularization parameter is too small, outliers can still influence the model's performance. Choosing the wrong epsilon value can also lead to a model that is either too lenient, ignoring important variations, or too strict, capturing unnecessary noise. Finally, SVR struggles with interpretability. Unlike simpler models such as linear regression, which provide clear coefficients that show the direct impact of each feature, SVR works in a transformed feature space, making it harder to understand the exact relationship between variables. This makes it less ideal for applications where explainability is crucial, such as medical diagnostics or regulatory environments where models need to be transparent. Despite these challenges, SVR remains a powerful tool when used in the right conditions. The key to making the most of it is understanding when it works best and knowing how to fine-tune its parameters to avoid pitfalls. But where exactly is SVR used in the real world, and why do industries rely on it for critical predictions? Let's explore its real-world applications next. Support vector regression isn't just a theoretical concept. It's actively shaping industries, helping businesses, researchers, and analysts make precise, data-driven predictions. Its ability to handle complex, high-dimensional, and noisy data makes it one of the most powerful tools in machine learning. Let's take a look at how SVR is being used across different fields to solve real-world problems. One of the most well-known applications of SVR is in finance, particularly for stock price prediction. The stock market is volatile, full of unpredictable fluctuations, and traditional linear regression models often struggle to capture its complexity. SVR, with its ability to model nonlinear relationships, helps analysts predict stock movements by learning from historical price trends, trading volumes, and macroeconomic indicators. Because SVR can ignore minor fluctuations while still capturing significant trends, it is especially useful for long-term forecasting. SVR is also making an impact in healthcare, where it is used to model disease progression. Medical researchers analyze patient data, including vital signs, lab results, and genetic markers, to predict how a disease might develop over time. For example, SVR can help doctors estimate how long a cancer patient might remain in remission, allowing them to adjust treatment plans accordingly. It is also used in personalized medicine, predicting how individual patients will respond to different drugs based on their genetic profiles. In environmental science, SVR plays a crucial role in pollution level forecasting. Governments and environmental agencies use SVR to predict air pollution levels based on historical data, weather patterns, and industrial activity. By understanding how pollution fluctuates over time, cities can implement proactive policies to reduce emissions and warn citizens about hazardous air quality levels in advance. Another field where SVR shines is engineering, particularly in system optimization. Manufacturing industries use SVR to predict the outcomes of different machine settings, allowing engineers to fine-tune processes for maximum efficiency. In automotive engineering, SVR is used to estimate fuel consumption and vehicle performance under different driving conditions, helping manufacturers build more fuel-efficient cars. In marketing and business analytics, SVR is used to predict customer behavior. Companies analyze past purchase history, browsing patterns, and customer interactions to forecast future buying trends. Retailers can use SVR to optimize pricing strategies, improve inventory management, and personalize marketing campaigns. By predicting what customers are likely to buy next, businesses can increase revenue and enhance customer satisfaction. The common theme across all these applications is that SVR allows industries to make more precise, reliable, and adaptable predictions. Whether it's forecasting financial trends, improving healthcare outcomes, optimizing engineering processes, or enhancing customer experience, SVR is transforming the way organizations make decisions. Now that we've seen where SVR is making an impact, the next step is understanding how to actually implement it. How do we take a dataset, apply SVR, and make accurate predictions? Let's walk through the process step by step. Implementing support vector regression may seem complex at first, but when broken down step by step, it follows a logical and structured process. To build an effective SVR model, we need to go through several key stages: preparing the data, selecting the right kernel, training the model, tuning the parameters, and evaluating its performance. Each of these steps plays a critical role in ensuring that the model is both accurate and reliable. The first step is data pre-processing, which is all about getting the dataset into the right shape. Real-world data is rarely clean. There are missing values, inconsistent formats, and varying scales across features. To ensure the SVR model performs well, we need to clean the data, handle missing values, and normalize or standardize numerical features. Normalization is particularly important because SVR is sensitive to the scale of the data. If one feature has values in the range of thousands and another is between 0 and 1, the model may give too much importance to the larger values. Standardizing the data ensures that every feature contributes equally to the prediction. Once the data is prepared, the next step is selecting the kernel function. The kernel defines how the model interprets the relationship between the input features and the target variable. If the data has a simple linear relationship, a linear kernel may be sufficient. However, in most real-world cases, relationships are more complex, and we may need to use a polynomial kernel or a radial basis function, RBF kernel. The right choice of kernel is crucial because it determines how well the model captures the underlying patterns in the data. After choosing the kernel, we move on to training the SVR model. The model learns by identifying support vectors, which are the most important data points that define the regression function. Instead of simply minimizing errors, SVR looks for the best possible function that fits within an acceptable margin of tolerance. During training, the model continuously adjusts its internal parameters to achieve the best balance between precision and generalization. But training alone is not enough. To improve performance, we need to tune hyperparameters such as the regularization parameter C, the epsilon margin, and the kernel-specific parameters. The regularization parameter controls how strict or lenient the model is in fitting the data. A small C value allows more flexibility and avoids overfitting, while a larger C forces the model to fit the training data more closely. Epsilon determines how much deviation from the true value is acceptable before the model considers it an error. A well-chosen epsilon ensures that minor fluctuations in data are ignored, keeping the model from overreacting to noise. Hyperparameter tuning is typically done using cross-validation, which helps identify the best combination of values to achieve optimal results. Once the model is trained and fine-tuned, the final step is evaluating its performance. The goal is to check how well the model generalizes to new, unseen data. Common evaluation metrics include mean squared error, MSE, which measures the average squared difference between predicted and actual values, and R-squared, which indicates how much of the variance in the data is explained by the model. If the error is too high, adjustments may be needed, such as reselecting features, tuning hyperparameters, or choosing a different kernel. By following this structured approach, we can build a powerful SVR model capable of making accurate predictions, but one key decision can make or break the entire process: choosing the right kernel. How do we decide which kernel is best for a given dataset? Let's explore that next. Choosing the right kernel is one of the most important decisions when working with support vector regression. The kernel function determines how the model interprets the relationships within the data and whether it can capture complex patterns. Picking the wrong kernel can lead to poor performance, while selecting the right one can dramatically improve accuracy. So how do we decide? The first step is understanding the nature of the data. If the relationship between input variables and the target variable is mostly linear, the linear kernel is the best choice. This is the simplest kernel and works well when the data set does not have strong interactions or complex structures. It is also computationally efficient, making it a good option for high-dimensional datasets where the number of features exceeds the number of observations. However, many real-world problems involve interactions between features, meaning that a straight-line relationship isn't enough. In such cases, the polynomial kernel can be a better choice. It allows the model to capture interactions between features by mapping them into higher dimensional space. The degree of the polynomial needs to be carefully chosen. Higher degree polynomials can model complex relationships, but can also lead to overfitting. For datasets with highly nonlinear relationships, where the pattern is difficult to describe with simple transformations, the radial basis function RBF kernel is often the best choice. The RBF kernel transforms the input space in a way that allows the model to identify hidden structures in the data. It is particularly useful when the relationship between variables is not obvious or when there are clusters in the data that traditional regression models struggle to capture. The RBF kernel introduces a new parameter, gamma, which controls how much influence a single data point has. A high gamma value makes the model sensitive to individual points, which can lead to overfitting, while a low gamma value results in a smoother model that generalizes better. There is no universal rule for selecting the best kernel, but there are some guidelines. If the data is simple and mostly linear, start with the linear kernel. If interactions between features are important, try the polynomial kernel. If the data is highly complex and nonlinear, the RBF kernel is usually the safest bet. In practice, the best approach is to test multiple kernels and compare their performance using cross-validation. Grid search, or random search, can help automate this process by testing different combinations of kernel types and hyperparameters to find the optimal configuration. Beyond just choosing a kernel, domain knowledge also plays a key role. Understanding the dataset, the relationships between features, and the expected behavior of the model can help guide the selection. In some cases, a simple kernel may work just as well as a complex one, and adding unnecessary complexity can lead to overfitting. Selecting the right kernel is a critical step, but it is just one part of fine-tuning the model. To truly optimize SVR for the best possible performance, we need to go deeper into hyperparameter tuning. How do we adjust parameters like C, epsilon, and gamma to create a model that balances accuracy and generalization? Let's find out next. Fine-tuning an SVR model is like adjusting the settings on a high-performance machine. Every small tweak can make a significant difference. To get the best possible predictions, we need to carefully optimize the hyperparameters that control how the model behaves. The three most important parameters in support vector regression are C, epsilon, and gamma, and finding the right combination is the key to balancing precision and generalization. The regularization parameter C determines how much the model tries to fit the data. A small C value allows more flexibility, meaning the model prioritizes a smooth function over fitting every single data point. This helps prevent overfitting, where the model memorizes noise instead of learning the true pattern. On the other hand, a large C forces the model to fit the training data as closely as possible, minimizing errors but increasing the risk of overfitting. Finding the right C value is a trade-off. Too small, and the model may underfit, missing important trends. Too large, and it may become overly sensitive to small variations in the data. The epsilon margin plays a different role. It defines a tolerance zone where errors are ignored, allowing the model to focus only on deviations that truly matter. A small epsilon means the model is forced to make highly precise predictions, capturing even the smallest fluctuations in data. While this might sound ideal, it can lead to overfitting by making the model overly sensitive. A larger epsilon, on the other hand, allows a bit more flexibility, making the model more resistant to minor variations and better at generalizing to unseen data. Choosing the right epsilon depends on the application. If high precision is required, a smaller epsilon is better. But if the data contains noise, a larger epsilon helps maintain stability. For models using the radial basis function, RBF kernel, the gamma parameter controls how much influence each training point has on the prediction. A high gamma means that every training point has a strong effect, allowing the model to capture highly detailed patterns, but also increasing the risk of overfitting. A low gamma results in a smoother, more generalized model that captures broader trends rather than individual variations. This is especially important for datasets with nonlinear relationships, where finding the right balance is crucial. So how do we find the best values for these parameters? The most effective approach is to use grid search or random search. In grid search, we define a range of possible values for C, epsilon, and gamma, and the model systematically tests all combinations to identify the best performing set. While this guarantees an optimal result within the selected range, it can be computationally expensive. Random search, on the other hand, selects random combinations of hyperparameters covering a broad range without testing every single possibility. This often leads to a good result while being more efficient than grid search. Another essential technique is cross-validation, which helps ensure that the chosen parameters generalize well to unseen data. Instead of training the model on a single dataset, cross-validation splits the data into multiple subsets, training on some while testing on others. This process is repeated several times, providing a more reliable estimate of how well the model will perform on new data. Hyperparameter tuning is one of the most critical steps in building an SVR model. A well-tuned model can achieve impressive accuracy, but a poorly tuned one can fail even if the data is strong. Once we've optimized these settings, the final step is to measure how well the model performs. How do we evaluate SVR predictions, and what metrics tell us if the model is truly effective? That's what we'll explore next. Once we've trained and fine-tuned our support vector regression model, the next crucial step is to evaluate how well it performs. A model might seem great during training, but if it doesn't generalize well to unseen data, it won't be useful in real-world applications. To measure the effectiveness of an SVR model, we rely on key performance metrics that tell us how accurate and reliable its predictions are. One of the most widely used metrics is mean squared error, which measures the average squared difference between the predicted values and the actual values. The lower the mean squared error, the better the model is at making precise predictions. Since this metric squares the differences, larger errors have a greater impact, making it particularly useful when we want to penalize large deviations. However, because squared errors can exaggerate the impact of outliers, we also look at other evaluation metrics to get a complete picture. Another important measure is R-squared, which tells us how much of the variance in the data is explained by the model. An R-squared value of 1 indicates a perfect fit, meaning the model explains all variations in the target variable. A value close to 0 means the model is barely better than simply predicting the average of the dataset. If the R-squared value is negative, it suggests the model is performing worse than a basic average-based prediction, indicating that adjustments may be needed. To ensure the model generalizes well, we use cross-validation scores. Instead of evaluating the model on just one test set, we divide the data set into multiple parts and test the model on different subsets. This process is repeated several times, and the average score gives a more reliable estimate of performance. Cross-validation helps prevent overfitting, where a model performs well on training data but fails on new data. If the cross-validation scores are significantly lower than the training scores, it's a sign that the model might be memorizing patterns instead of learning general trends. Evaluation is not just about checking numbers, it's about interpreting the results and understanding how the model behaves in different conditions. If the mean squared error is too high, we may need to fine-tune parameters like C, Epsilon, or the choice of kernel. If the R-squared value is low, it might indicate that the selected features are not providing enough useful information, requiring better feature engineering. If cross-validation scores show significant variation, it might suggest that the model is too sensitive to certain data points, meaning adjustments in regularization or data preprocessing might be needed. Evaluating SVR is not just a one-time process. It's an iterative cycle of analyzing performance, making improvements, and refining the model until it reaches the desired accuracy. Now that we know how to measure performance, it's time to bring everything together and apply SVR in practice. Let's step into the world of Python and see how we can implement support vector regression with real data. Now that we've explored the theory behind support vector regression, it's time to bring it to life with a hands-on implementation in Python. With the power of scikit-learn, pandas, and NumPy, setting up an SVR model is straightforward. Let's walk through the process step by step and see how we can train an SVR model to make real-world predictions. The first step is loading and preparing the data. Using pandas, we load the dataset, inspect its structure, and check for missing values. Missing data must be handled either by filling in gaps with appropriate values or removing incomplete entries. One of the most important pre-processing steps is feature scaling, since SVR is sensitive to differences in magnitude across features. We use standard scaler or min-max scaler from scikit-learn to normalize or standardize the data, ensuring all features contribute equally to the model. Once the data is clean, we split it into training and testing sets. This allows us to evaluate how well the model generalizes to new, unseen data. The train test split function from scikit-learn makes this easy, typically dividing the dataset so that 80% is used for training and 20% for testing. Next, we initialize the SVR model. The first key decision is choosing the kernel function. If the relationship between the input features and target variable is approximately linear, a linear kernel is the best choice. If interactions between features matter, a polynomial kernel might work better. For nonlinear relationships, the radial basis function, RBF kernel, is the most commonly used option. We also set initial values for C, Epsilon, and Gamma, which we will fine-tune later for optimal performance. Now it's time to train the model. We fit the SVR model to the training data, allowing it to learn patterns and identify the most important support vectors that define the regression function. Once trained, we use the predict function to generate predictions on the test data. Finally, we evaluate the model's performance using key metrics. Mean squared error, MSE, helps us measure the average squared difference between the predicted and actual values. A lower MSE indicates better predictive accuracy. We also calculate R squared, R2, to determine how well the model explains the variance in the dataset. If the results aren't satisfactory, we fine-tune the model by adjusting hyperparameters like C, Epsilon, and Gamma, or by trying different kernel functions. By following these steps, we can build an effective SVR model that can be used for tasks like predicting stock prices, modeling disease progression, or optimizing engineering processes. But how does SVR compare to other regression techniques like linear regression or decision tree regression? Let's find out next. Support vector regression is a powerful tool, but how does it stack up against other regression techniques? Understanding its strengths and weaknesses compared to alternatives like linear regression and decision tree regression helps us make inform decisions about when to use SVR and when another method might be better suited. Let's start with linear regression, one of the most widely used regression techniques. It is simple, fast, and easy to interpret, making it a go-to choice for many applications. However, it has a significant limitation. It assumes a straight-line relationship between input features and the target variable. If the data has complex nonlinear patterns, linear regression struggles to provide accurate predictions. SVR, on the other hand, can model both linear and nonlinear relationships using different kernel functions, making it much more flexible. Another major difference is how errors are handled. Linear regression minimizes the total squared error, meaning it tries to fit every data point as closely as possible. This can make it highly sensitive to outliers, which can pull the regression line in unintended directions. SVR, in contrast, introduces an epsilon margin where small errors are ignored, making it far more robust to noisy data. This allows it to focus on meaningful trends rather than being influenced by extreme values. Now let's compare SVR to decision tree regression. Decision trees break the dataset into smaller and smaller groups, creating a step-like function to approximate the relationship between inputs and outputs. The advantage of decision trees is that they are easy to interpret and naturally handle nonlinear relationships without requiring a kernel transformation. However, they tend to overfit easily, especially when the tree becomes too deep. SVR with proper regularization can strike a better balance between accuracy and generalization. Another key distinction is computational efficiency. Linear regression is the fastest method, as it involves only a simple mathematical formula. Decision trees can be relatively fast, but become computationally expensive with large data sets, especially when tuning parameters like depth and number of splits. SVR is often slower than both linear regression and decision trees, particularly when using nonlinear kernels, because it requires solving a complex optimization problem. This means that for very large datasets, simpler methods might be preferable unless the additional accuracy of SVR justifies the extra computation. When should we use SVR over these alternatives? If the data follows a clear linear trend, linear regression is the better choice due to its simplicity and speed. If the data is highly nonlinear and interpretability is important, decision tree regression may be preferable because of its intuitive structure. However, if we need a model that can handle both linear and nonlinear relationships while being robust to outliers, SVR is the ideal option. It is particularly useful for high-dimensional datasets, noisy data, and applications where precision matters more than speed. While SVR is a powerful regression method, it has its own challenges, particularly when dealing with outliers. These extreme values can still influence the model under certain conditions, and handling them properly is essential to getting reliable predictions. In the next section, we'll explore techniques for detecting and managing outliers in SVR models. Outliers are one of the biggest challenges in machine learning, and support vector regression, while robust, is not completely immune to their effects. Outliers are extreme values that deviate significantly from the rest of the data, and if not handled properly, they can distort the model's predictions. While SVR introduces an epsilon margin that helps ignore minor deviations, severe outliers can still influence the support vectors and impact the model's performance. To build a more reliable SVR model, we need to detect and manage these outliers effectively. The first step is outlier detection, identifying which data points may be problematic. One common approach is using statistical tests like the z-score or the interquartile range IQR method. The z-score measures how far a data point is from the mean in terms of standard deviations. A z-score beyond a certain threshold, such as 3 standard deviations, may indicate an outlier. The IQR method focuses on the spread of the middle 50% of the data and flags values that fall too far outside this range. These methods are useful for detecting extreme values in numerical data sets before they affect the SVR model. Another approach is using machine learning algorithms to detect anomalies. Techniques like isolation forest and DBSCAN, density-based spatial clustering of applications with noise, can help identify and filter out outliers before training the SVR model. These methods work by finding points that behave very differently from the majority of the data, making them ideal for datasets with complex structures. Once outliers are detected, the next decision is whether to remove or transform them. If an outlier is the result of an error, such as incorrect data entry, it should be removed. However, in cases where outliers contain valuable information, simply discarding them may not be the best approach. Instead, we can use robust scaling techniques, such as log transformations or winsorization, which limit the effect of extreme values by capping them within a reasonable range. Another option is adjusting the SVR hyperparameters, such as increasing the Epsilon margin to allow for more tolerance around predictions, reducing the influence of extreme values. Another strategy is using an alternative loss function. The standard epsilon insensitive loss function in SVR ignores errors within a margin, but for datasets with many outliers, other loss functions like Huber loss can be more effective. Huber loss combines the best of both squared loss and absolute loss, making the model resistant to extreme deviations while still capturing meaningful trends. Handling outliers is an essential step in building a high-quality SVR model. Ignoring them can lead to inaccurate predictions, while overreacting by removing too many points can result in lost information. The key is finding the right balance, detecting outliers effectively, deciding whether to remove or transform them, and fine-tuning the model's parameters accordingly. Outliers are just one challenge in predictive modeling, but what happens when we need to forecast values over time? Support vector regression is often used for time series forecasting, but applying it to sequential data comes with its own unique challenges. Let's explore how SVR can be adapted for predicting trends over time in the next section. Time series forecasting is one of the most important applications of machine learning, and support vector regression can be a powerful tool for predicting future trends. Unlike traditional regression models that assume independent data points, time series data is sequential, meaning that past values influence future outcomes. To successfully apply SVR for time series forecasting, we need to prepare the data properly, engineer meaningful features, and fine-tune the model for sequential predictions. The first step is data preparation. Time series data often contains missing values, seasonal patterns, and trends that must be handled before training the model. Cleaning the data involves filling in missing values using interpolation or forward filling techniques to maintain consistency. Since SVR does not inherently understand time-based sequences, we also need to normalize or standardize the features to ensure that all input variables contribute equally to the prediction process. Feature engineering is a critical step in making SVR work well for time series forecasting. Unlike models specifically designed for sequential data, such as LSTMs, SVR requires transforming time-dependent relationships into structured input features. One way to do this is by creating lag features, which introduce past observations as new variables in the dataset. For example, instead of directly predicting tomorrow's stock price, we can include the stock prices from the past 7 days as input features, allowing SVR to learn from previous trends. Additionally, rolling statistics, such as moving averages, can help capture long-term patterns by smoothing fluctuations in the data. Choosing the right kernel function is crucial when applying SVR to time series forecasting. If the time series has a simple linear trend, a linear kernel may be sufficient. However, financial data, weather patterns, and economic indicators often exhibit complex, non-linear relationships. In such cases, the radial basis, function, RBF kernel, is usually the best choice because it captures hidden patterns that are not immediately obvious. The gamma parameter in the RBF kernel determines how much influence each past data point has on the predictions. Too high, and the model overfits. Too low, and it fails to capture important trends. Once the model is trained, evaluating its performance requires using metrics tailored for time series forecasting. Mean absolute error, MAE, and root mean squared error, RMSE, are commonly used to measure how far off the predictions are from the actual values. Since time series models are used for making decisions about the future, cross-validation is performed differently compared to traditional regression tasks. Instead of random splits, we use time-based cross-validation, where the model is trained on past data and tested on future data to simulate real-world conditions. Despite its strengths, SVR has some limitations in time series forecasting, since it does not inherently model sequential dependencies like recurrent neural networks. It relies entirely on the lag features and engineered variables provided. If the chosen features do not fully capture the time-based relationships, the model's predictions may suffer. Additionally, training SVR on very large time series datasets can be computationally expensive, especially with nonlinear kernels. However, when properly tuned, SVR can be highly effective for time series forecasting, particularly in scenarios where traditional regression models fail and deep learning approaches are too resource intensive. From predicting stock prices and energy demand to forecasting sales trends and climate patterns, SVR provides a flexible and interpretable alternative for making time-based predictions. But how well does SVR perform in real-world applications? To see its impact, let's explore a case study where SVR has been used in financial market prediction. How well can it forecast stock prices, and what lessons can we learn from its results? Let's find out next. Support vector regression has been widely applied in financial market prediction, where accurately forecasting stock prices, currency exchange rates, and other financial trends can provide a competitive edge. The stock market is a complex system influenced by countless variables: economic indicators, company performance, investor sentiment, global events, and market fluctuations. Traditional regression models often struggle with the non-linearity, volatility, and noise in financial data. This is where SVR shines, offering a robust approach to capturing patterns while ignoring minor fluctuations. In a case study on stock price prediction, researchers gathered historical stock prices and trading volumes from sources like Yahoo Finance and Bloomberg. To enhance prediction accuracy, they incorporated additional economic indicators such as interest rates, inflation rates, and geopolitical events. Since stock prices follow complex nonlinear trends, a radial basis function, RBF kernel, was chosen, as it allows SVR to map the data into a higher dimensional space where hidden relationships become more apparent. Before training the model, the data was cleaned and normalized. Missing values were handled using interpolation methods, and numerical features were scaled to ensure that all inputs contributed equally to the model's learning process. Feature selection played a crucial role. Besides historical prices, researchers engineered features like moving averages, momentum indicators, and relative strength index, RSI, all of which helped capture patterns in market behavior. To evaluate performance, the dataset was split into 80% training data and 20% testing data, ensuring that the model learned from past trends before making predictions on unseen data. Time-based cross-validation was applied to simulate real-world trading scenarios where predictions were continuously tested against new stock price movements. The SVR model was initialized with an RBF kernel, and hyperparameters were tuned using grid search to find the optimal values for C, epsilon, and gamma. The regularization parameter C was adjusted to prevent overfitting, while epsilon controlled how much deviation from the actual stock price the model was willing to tolerate before penalizing errors. Gamma was fine-tuned to determine how much influence each data point had on predictions. After training the model, predictions were generated for future stock prices, and the results were compared against real market values. The model's performance was evaluated using mean absolute error, MAE, and root mean squared error, RMSE. The final results showed an MAE of 0.15 and an RMSE of 0.25, indicating that the SVR model was able to make reasonably accurate predictions. When backtested against historical stock data, the model achieved an 85% predictive accuracy, meaning that in most cases it correctly estimated the direction of stock price movements. However, the study also revealed some limitations. While SVR performed well in short-term forecasting, it struggled with long-term predictions due to market unpredictability and external factors that could not be modeled directly. Additionally, the model's accuracy depended heavily on feature selection, including the right economic indicators significantly improved predictions, while irrelevant or misleading data reduced performance. Key takeaways. SVR is highly effective for short-term stock price forecasting, especially when combined with the right features and an RBF kernel. Feature engineering is critical. Incorporating technical indicators and economic factors improves accuracy. Hyperparameter tuning plays a major role. Adjusting C, epsilon, and gamma ensures a balance between flexibility and precision. SVR struggles with extreme volatility and long-term predictions, making it better suited for short-term trend analysis. This case study demonstrates the power of SVR in financial market prediction, but also highlights the importance of careful data, pre-processing, feature selection, and model tuning. While SVR provides a strong foundation, combining it with ensemble methods or deep learning techniques could further enhance its predictive capabilities. Financial forecasting is just one of many areas where SVR is making an impact. In the next section, we'll explore how SVR is being used in healthcare, where predicting disease progression and patient outcomes is crucial for improving medical treatments and decision-making. Support vector regression is not only useful in finance, but is also making a significant impact in healthcare, where accurate predictions can save lives. In medical research and clinical decision-making, predicting patient outcomes, disease progression, and treatment effectiveness is crucial. Traditional statistical models often struggle with the complexity and variability of medical data, but SVR provides a flexible and robust approach to making precise predictions. One major application of SVR in healthcare is disease progression modeling. Chronic diseases such as diabetes, cardiovascular conditions, and neurodegenerative disorders evolve over time, and understanding how they progress can help doctors make better treatment decisions. By analyzing historical patient data, including biomarkers, lifestyle factors, and genetic predispositions, SVR can predict the trajectory of a disease. This allows doctors to identify high-risk patients early, personalize treatment plans, and improve long-term outcomes. Another critical area where SVR is used is patient outcome prediction. Hospitals and medical researchers analyze data from thousands of patients to determine how different factors influence recovery times, treatment success, and the likelihood of complications. In a study involving 500 patients undergoing post-surgical treatment, SVR was used to predict recovery times based on demographic information, pre-existing conditions, and post-operative care. The model achieved an accuracy of 85% in forecasting recovery outcomes, helping doctors allocate resources more effectively and improve patient care. One of the biggest advantages of SVR in healthcare is its ability to handle high-dimensional data. Medical data sets often contain hundreds or even thousands of variables, from lab test results to imaging data, and many machine learning models struggle with this complexity. SVR, with its ability to work in high-dimensional spaces, can process these vast data sets while maintaining strong predictive performance. Additionally, its robustness to outliers makes it particularly useful in medical applications where variations in patient data are common. However, SVR also has limitations in healthcare. Medical data is often noisy and incomplete, and while SVR can handle some degree of missing information, preprocessing is essential. Additionally, interpretability is a challenge. Unlike simpler models, such as linear regression, which provide clear coefficients explaining the impact of each variable, SVR operates in a transformed feature space, making it harder for doctors to directly interpret how specific factors influence predictions. This can make it difficult to justify treatment decisions based purely on SVR outputs. Despite these challenges, SVR is proving to be a valuable tool in modern medicine. From predicting disease progression to optimizing hospital resource allocation, it is helping healthcare professionals make more data-driven and accurate decisions. As machine learning continues to evolve, combining SVR with deep learning techniques and integrating real-time patient data could further improve medical predictions. The ability of SVR to handle complex, high-dimensional data makes it useful not just in healthcare but in many other scientific fields. But where is SVR research heading next? What advancements are being made to improve its performance, scalability, and integration with other machine learning techniques? Let's explore the future of SVR in the next section. Support vector regression has already proven to be a powerful tool in various fields, but research is continuously evolving to push its capabilities even further. As datasets grow larger and problems become more complex, new advancements are being made to improve SVR's performance, scalability, and integration with other machine learning techniques. One of the most exciting directions in SVR research is its integration with deep learning. Traditional SVR models rely on manually engineered features, which can limit their ability to detect hidden patterns in highly complex data. By combining SVR with deep neural networks, researchers aim to leverage deep feature extraction while maintaining the robustness and precision of SVR. In this hybrid approach, a deep learning model first extracts high-level features from raw data, and then SVR is used as a final regression layer to make precise predictions. This technique is being explored in areas such as medical diagnostics, financial forecasting, and image-based regression tasks. Another major advancement in SVR research is improving scalability. While SVR is efficient for moderate-sized datasets, its computational complexity increases with the number of data points, making it challenging to apply to big data problems. New algorithms such as approximate SVR and parallelized SVR aim to reduce the computational burden by approximating support vectors more efficiently. Researchers are also exploring distributed computing frameworks where SVR is implemented across multiple processing units or cloud-based systems to handle large-scale datasets without significant slowdowns. Beyond improving speed, there is also a push toward developing more adaptive kernel methods. Kernels define how SVR transforms data into higher dimensions, but selecting the right kernel still requires manual tuning. Researchers are working on automated kernel selection techniques, where the model dynamically chooses the best kernel based on the dataset's structure. There is also growing interest in designing hybrid kernels, which blend multiple kernel functions to improve performance across diverse datasets. Another area of exploration is making SVR more interpretable. While SVR produces highly accurate predictions, its inner workings are not as transparent as simpler models like linear regression. Efforts are being made to develop explainable SVR models, where the contributions of different features can be more easily understood. This is particularly important in fields such as healthcare and finance, where decision-making needs to be both accurate and justifiable. As machine learning continues to evolve, SVR is expected to play a critical role in next-generation AI applications. Whether through deep learning integration, faster computation, improved interpretability, or smarter kernel selection, the future of SVR is focused on making it more powerful, scalable, and adaptable to a wider range of real-world problems. With all these advancements, it's clear that SVR is not just another regression model. It's a dynamic tool that continues to evolve. But before we wrap up, let's summarize everything we've covered and reflect on the key takeaways from support vector regression. Support vector regression is more than just another machine learning algorithm. It is a powerful, flexible, and precise tool that extends the principles of support vector machines to regression tasks. Throughout this exploration, we have seen how SVR can handle high-dimensional data, nonlinear relationships, and outliers, making it an invaluable asset in real-world applications. One of the biggest strengths of SVR is its ability to balance precision and generalization. Unlike traditional regression models that minimize every error, SVR introduces an epsilon margin, allowing it to focus only on significant deviations while ignoring minor fluctuations. This makes it especially useful in fields where data is noisy or incomplete. SVR has proven its effectiveness across multiple domains. In finance, it helps predict stock prices with high accuracy, identifying market trends while filtering out random fluctuations. In healthcare, it models disease progression and patient outcomes, supporting better medical decision-making. In environmental science, it forecasts pollution levels, enabling proactive policy measures. Whether in engineering, marketing, or business analytics, SVR continues to play a critical role in making data-driven predictions. Despite its advantages, SVR is not without challenges. Hyperparameter tuning is crucial, as parameters like C, epsilon, and gamma significantly affect performance. Selecting the right kernel function is another key factor. Linear kernels work well for simple relationships, while RBF kernels capture more complex patterns. Additionally, computational efficiency can be a limitation, especially for large datasets, though ongoing research is addressing this with more scalable implementations. Looking ahead, the future of SVR is exciting. Deep learning integration is enhancing its feature extraction capabilities. Automated kernel selection is making it more adaptable, and distributed computing is improving scalability for big data applications. Efforts to improve model interpretability are also making SVR more accessible for critical decision-making in fields like healthcare and finance. At its core, SVR is a model that combines mathematical rigor with practical flexibility. Whether predicting future trends, optimizing systems, or making data-driven decisions, it remains one of the most reliable regression techniques in machine learning. As machine learning continues to evolve, support vector regression will remain a key player in predictive analytics, offering a robust and adaptive approach to tackling complex real-world problems.